Hello everybody and welcome to a new episode of Math for Fun. Today we're going to look at the greatest common denominator, a way to calculate it, and a way to generate a linear combination of the things that you're generating the greatest common denominator of. And then we're going to look at some math contest problems that where this is used, where it's useful as a technique to solve them. Okay. So starting with definitions, for positive integers a and b, the greatest common denominator of a and b equals r, implies that a is equal to n times r, k is equal to m times r, and the greatest common denominator of n and m is 1. So let's look at an example. The greatest common denominator of 34 and 51. Well, 34 is equal to 2 multiplied by 17. 51 is equal to 3 multiplied by 17. So the greatest common denominator is equal to 17, right? The largest common factor, very simply. So in situations where we can do these by examination, by inspection, it's pretty easy. But you can always find a greatest common denominator. That's something that's, I think, fairly obvious, but it's worth stating, that there is always one. But sometimes it's not so easy. If you have, for example, the greatest common denominator of 2049 and 17,638. What's the greatest common denominator? I don't know. But we are going to give you a technique that you can use to calculate greatest common denominators like this. So we're going to introduce this theorem, very basic, which is essentially a division algorithm. For any pair of positive integers, we can find an integer q, which is a quotient, and a non-negative integer r, bigger than 0, which is going to be less than b, such that a is equal to the quotient multiplied by b plus the remainder. So if we look at an example, 135 is equal to 2 multiplied by 60 plus 15. Now what makes this into an algorithm that we can use to calculate the GCD is that the GCD of the two bigger numbers, the two original numbers, is equal to the GCD of the smaller number and the remainder. Now why is this true? Well, let's think back to the definition of the GCD. If we have, in this case, 135 is equal to k times n, and 60 is equal to k times n, then 135 minus 2 times 60 is equal to k multiplied by m minus 2n. So if k divides 135 and 60, then it also divides the remainder. And we can also prove, but I'm not going to do it right here, that that you can't have a bigger GCD of 60 and the remainder than you have of the original two numbers. So we can write this as a is congruent to r modulo b. And we're going to get to modular arithmetic later. All you need to know is that a is congruent to r mod b is the same thing as a is equal to r plus k times b for some k in the natural numbers. So this gives us an algorithm that we can use to find a greatest common divisor. And what makes it even more interesting is it gives us a way to calculate as a linear combination some arrangement of the two original numbers. So let me start with a fairly simple example. I want to find a way to write 1 as a multiple of 13a as a linear combination of 13 and 17. Okay, so I want to find integers a and b such that 1 is equal to 13a plus 17b. Now, you might be able to do this by inspection, but if we get to much bigger numbers, it's going to be a lot more complicated. But we can use this algorithm because we know that 13 and 17 have a GCD of 1. Well, let's use this algorithm to to prove that 13 is equal to 3 multiplied by 4 plus 1. So we've got our GCD of 1. But now we can use these intermediate stages to generate a linear combination of 17 and 13. 1 is equal to 13 minus 3 multiplied by 4. That's clearly correct. And then we can replace 4 by 7 minus 13. 17 minus 13. So we end up with 13 plus 3 times 13 is 4 multiplied by 13 minus 3 multiplied by 17. And this linear combination, this way of calculating a linear combination of any two numbers, you can calculate the linear combination to their GCD. This is called Bezouts Identity, and it comes up all the time in math contests. And we can calculate whether this is true. 4 times 13 is 52. 3 times 17 is 51. We're golden. So we're going to do a couple of problems that use this technique. And then I'm going to give you some problems to do on your own, and I'll be available to help you if you need them, that also use this same idea of Euclid's algorithm and Bezouts identity. So find a positive integer n such that 3n is equal to 1 mod 14. Well, this is the same as calculating 3n plus 14m equals 1. So let's use our technique to get the greatest common denominator of 14 and 3. 14 is equal to 4 times 3 plus 2. 3 is equal to 2 plus 1. So then we've got 1 is equal to 3 minus 2 is equal to 3 minus 14 minus 4 times 3. So n is equal to 5. Because 15 minus 14 is equal to 1. Now that's a fairly simple one. You could probably have found that on your own, but we'll see that it gets a lot more complicated. What's the inverse of 10 modulo 17? Well, this means we've got to find a number n that's equal to 1 modulo 17. That's what the inverse is, right? 10 multiplied by its inverse is 1. Well, again, this is 10n plus 17m is equal to 1. And we can again use this algorithm. 17 is equal to 10 plus 7. 10 is equal to 7 plus 3. 7 is equal to 2 times 3 plus 1. And then working it in reverse, 1 is equal to 7 minus 2 times 3 is equal to 7 minus 2 times 10 minus 7, which is equal to 3 times 7 minus 2 times 10. (21 minus 20), so that's correct, is equal to 3 times 17 minus 10 minus 2 times 10. So we end up with 3 times 17 minus 5 times 10, 51 minus 50, and the inverse of 10 modulo 17 is minus 5. But when we're dealing with modulo 17, we're dealing with just remainders, so we can have that as 17 minus 5, or 12. And let's see if that works. 10 multiplied by 12 is equal to 120, and 17 multiplied by 7 is equal to 119. So we do indeed have a number that when you multiply by 10 gives you 1 mod 17. So these are your homework questions. Just to go over the vocabulary, a Diophantine equation is an equation where the solutions are all in integers. So all of these are going to be the same idea, that we're going to find an integer solution to the first equation. We're going to find a natural number that's a positive integer solution to the second equation, such that the expression here is also a natural number. And then finally, this is a kind of a cute problem that I'll give you a hint for. Find the smallest positive integer that ends in 2010 and is divisible by 2011. So if a number ends in 2010, that means it is 10,000 multiplied by some number n plus 2010. And you want that to be equal to 2011 times some number m. And you should be able to work it out from there. So good luck, and I'll see you at our next episode.